Hello, I'm Eric from OpenZeppelin. I'm one of the security auditors there, blockchain security researcher, and I've gone over the Zama contracts pretty extensively.
Hi, I'm Thomas. I work at Zaiffer. I handle all of the backend and smart contract development, and hopefully you'll enjoy the talk. So here, what we'll go about real quick is, since we're going to be discussing confidential tokens, I'll be detailing from a developer's perspective the sort of primitives that you'll be manipulating as a smart contract developer on the Zama ecosystem, and so that includes all of the encrypted entities that you might manipulate, and also how it actually works under the hood. So keep in mind, I'm not a Zama core developer, obviously. So the whole goal is that you understand these primitives from the smart contract developer's perspective, and not from a FHE mathematician, I guess. Do you want to say a word?
Oh yeah, and then after he explains that, I'll be going into some of the OpenZeppelin contracts that are built on the Zama stack. I'll be talking about ERC-7984, which is the confidential token standard, some of our extensions, and then some secure design tips so that you don't get wrecked.
Okay, so what's an encrypted type? They're encrypted versions of your favorite solidity types. So you'll have in solidity, obviously, unsigned ends, addresses, etc. And so what you can do using FHE VM is have the encrypted version of these types. Sorry. So what you have to watch out for in these types is that you'll often see this in the FHE VM jargon, the word handles. So you don't actually have the encrypted value of your variable on chain. What you have is some sort of pointer that points to an off-chain, I guess, database with all of the encrypted values to your variables. And so this is very important to understand because it has a lot of implications when you develop your smart contracts. So yeah, for instance, all of these new types will have their specific operations. So when you have regular uints in Solidity, and you can just use the plus operator, here you have to use to go through some special FHE library that allows you to operate on your encrypted types. And yeah, obviously, as I said, all the operations are asynchronous since the values are not themselves on-chain. So there's something that you need to watch out for when you're manipulating these encrypted types is everything that's overflows and whatnot. Again, since the operations are asynchronous, overflows are also somewhat asynchronous. That means that you cannot, when you use OpenZeppelin safe math, for instance, on regular solidity types, if you have overflows, you'll have a reversion on your smart contract, and that gives you a bunch of security paradigms that you can implement and ensure that your contracts will revert whenever you have some sort of problem. In FHE VM types, that's not the case. It's a bit harder to do, and so OpenZeppelin has implemented another library that works essentially the same way, but that's specifically designed for these new types. So instead of reverting, they'll have to return some sort of type, and they'll return whether the addition or the subtraction was indeed successful or not. And this, it returns as an encrypted type itself. So here, for instance, I've got a small example where, if I use safe math, try increase, and it overflows, I'll get a reversion in Solidity. In FHE, it'll actually return me with an encrypted Boolean that here I've called eSuccess. And then what I can do is actually condition on this value, and either here, for instance, I'm increasing the total supply. If my encrypted total supply overflows, I'll have a faulty encrypted success result. And in the transfer amount, I'll actually transfer 0. Because here I have to transfer 0 since I cannot first revert at this point. And second, I don't actually know the value, the value of this addition. I don't actually know it. So I have to go through, and I'm using this special branching mechanism from FHE, where instead of using just a regular if-else construct like I would in regular Solidity, I have to use this sort of function that builds a symbolic execution tree of my calculation. So with encrypted types, you also have the concept of ACLs, who's allowed to manipulate your encrypted types. So this is fairly important. For instance, when you have an encrypted type, a smart contract has some sort of encrypted type and wants to send it to some other contract to operate on it. Cross-contract communication is something fairly classic in Solidity and in smart contract development. But here you need to actually give access to the contract you're sending that value to, so that they can manipulate the encrypted type. So you have multiple ways to do this. You can either give it a permanent access to the handle. If you remember the handles, the on-chain representation of the encrypted type, or you can give it a transient allowance so that it only has the right to operate on it during the execution of the transaction. You also have a way for a contract to know if whatever contract is sending it an encrypted type has the right to send you that encrypted type. Because people could just watch the blockchain, retrieve some values, and send it to your contract and somewhat attack it like this. So best practice is to verify that the sender sending you the encrypted type has the right to manipulate that value. Okay, so now that I've talked about permissions and stuff like that, so how do you actually implement a function that operates on encrypted arguments? So there are two ways, meaning that you'll often have to implement your functions in two separate ways because they'll have two separate signatures. So here the first method is you pass an encrypted type to your smart contract. So smart contract A has some encrypted value, wants to send it to smart contract B. You'll just send it to that function that accepts it as an argument. So you'll have the FHE allowances and sender verifications that you'll put into place. But you also have a second method, which is when some regular accounts, non-smart contract accounts, wants to call a smart contract, you'll need to do some special initialization and also generate some sort of proof to ensure that you know what you're actually sending. And so that's the second method. In practice, what it means is that you have different arguments when it's when the encrypted value for your argument was first created off-chain, or whether it's something that already exists on-chain and you're passing it from a smart contract to another smart contract. So yeah, again, it's something that's important to remember this asynchronous execution of your encrypted type values. So here, in the context of a token, a regular ERC-20 token, you'll just do you'll have some balances. You'll increase and decrease the balances and the total supplies. Here, you'll essentially do the same thing, except that all of the calculations are done off-chain. So on-chain, what you'll have is a symbolic tree that builds the computation to be executed. And this will be read off-chain by the Zama systems, by the FHE VM systems, that will read whatever, but that will reproduce off-chain that execution in the exact same order it appeared on-chain to ensure that they maintain the same states. And so one of the nice things about this is that your smart contract is not, the execution since the execution is merely building a computational graph, it's not slowed down. One of the drawbacks, obviously, is that if you want to then decrypt an FHE value, you'll need to wait for the Zama systems to have executed the symbolic computation you define during the execution of your smart contract. Okay, and so here we have something that's definitely very important, and that seemed very weird for me at the beginning when implementing smart contracts in FHEVM.
Yeah.
In the encrypted types, you're in encrypted world, and turns out everything's much more expensive. So when in Solidity, manipulating a uint 256, as you do in an ERC-20, for instance, is something that we've all been doing forever, and we wouldn't even think about the consequences of doing so. In FHE, it's generally considered too expensive, or sufficiently expensive that you shouldn't use it everywhere. And as Eric will explain it, in the encrypted equivalent of the ERC-20 contracts, we're actually using uint 64. And so you kind of have this natural mapping where you usually values that would be 256 in, and so actually when you think about it, uint 64 is definitely sufficiently large. You'll just have to, for instance, in the token context, instead of having your tokens be 18 decimals, you just make them 6 decimals, and it's usually way sufficient. All right, here you go, Eric.
Yeah, so OpenZeppelin has built off of the Zama stack and developed the ERC-7984 standard. It's still in ERC stage, so it could change a little bit, but we don't think it really will. Basically, this is a confidential token. So it provides a few functions that I've listed here. This isn't all of the API, but there's confidential transfers and confidential transfer froms. These are your ERC-20 transfer and transfer from functions, except that the amount itself is encrypted. So this is an encrypted type. Notably, the sender and receiver are in plain text, and this is for compliance purposes, so that you can prove you're not sending to like bad guys or something on chain, but also so that event emissions in block explorers can be logged. Still emits like that transfer event. There's also confidential transfer, from and call. And this is really important because going back to the idea of FHE allowances, which is the ability to see and modify an encrypted value, the contract being called will also need to have that allowance and be able to do something with that value before you're done with the transfer. If you don't provide that, the contract or EOA that's receiving these tokens basically won't be able to do anything with the amount of tokens you've transferred them. So this allows you to give them permission, and then you could even give them transient permission so that it's just available for that transaction execution, and then they can do something with it. So you do a call into that contract, and it can do some operations on this encrypted value before the transaction is through. So you need to implement this on confidential transfer received function if you want to make a contract that receives ERC-7984 tokens. And if there is a failure for whatever reason in your contract, because we can't revert when we're in FHE land, you can return a encrypted Boolean that the ERC-7984 token can do something with. And that Boolean just says like whether or not the transfer succeeded. And so that we don't reveal information because this is all supposed to be confidential. If there is a failure, the tokens will be refunded to the sender, so they won't be actually sent. But we can't know that if we're looking at it in the plain text land. So we just include that encrypted Boolean, and then if it's false, that basically means the tokens have actually been refunded to the sender and never made it to the recipient. And then there is the request and disclose encrypted amount functions. So these are two separate functions. And basically what they mean is if you are allowed to see that encrypted value, you can request that the FHEVM creates a proof of what that value is, and then you can disclose it, or you take that proof and you put it on chain and you prove to the whole world that this encrypted value equals this plain text value. And that's really important if you're moving tokens into or out of a confidential token wrapper, so that you can basically get them out and say, yes, I had 100 tokens and now I'm unwrapping them into a regular ERC-20. There's also, of course, your confidential balance of, confidential total supply. These will assume that whoever's calling them has allowance permissions. And there is operator-based approval. So this is like approve in ERC-20, except it doesn't include any amounts. It's just saying that somebody has the ability to modify your account. And that's by design. Again, if we included amounts, that would reveal some information about the current balance of the account in question. So we've also got a couple extensions in the OpenZeppelin confidential contracts library. Go check it out on GitHub. I don't know if we linked it in here, sorry. But one of the extensions is ERC-7984 Omnibus. So if you recall, I mentioned in the last slide that the users are not encrypted. So when you send and receive tokens, those addresses are actually visible on chain. This is for compliance purposes. This Omnibus kind of provides a bit of a workaround. So it still transfers tokens to and from accounts that are visible on chain. However, there's an encrypted sender and recipient. I'm not sure exactly how to refer to this, so I'll call it the meta sender and meta recipient. Basically, this is designed to say, if I'm transferring to Ma on behalf of somebody else, I can say, hey, just so you know, earmark these funds for that person, that recipient. And the idea is that, for example, exchanges could use this. So they could transfer funds between each other. One exchange transfers to another exchange, and this is logged on chain, and everyone can see that that transfer happened. But they could say hey, these funds are coming from this account and going to this account, and then off chain that exchange knows to credit, those accounts. So yeah, it's all about compliance. Sadly, we still have to pay attention to that. But I've just highlighted here the encrypted sender, this E, and the encrypted recipient. But as you can see down here, it really just is a regular confidential transfer from and call using the plain text omnibus from and omnibus to addresses. There's also the ERC-20 wrapper. So this is basically a way to convert your ERC-20 token into an ERC-7984 confidential token. It has ERC-1363 support. Basically, this just means that it has an on-transfer received hook. So if you just send tokens directly to the ERC-20 wrapper, it will automatically wrap them into ERC-7984, assuming that you are calling this on-transfer received hook, which OpenZeppelin contracts do. It wraps amounts to the EUINT64, which, as we discussed earlier, that's smaller than the typical EUINT 256. So it will automatically check the decimals of your ERC-20 token and basically downscale whatever amount you're sending in there to 6 decimals, so that it fits in the EUINT64 nicely. And then there is the 2-stage unwrapping. So the first call, unwrap, will burn the confidential tokens that you are unwrapping, and then it will basically ask the FHE VM for a decryption proof. And then once you've got that, you can feed it into the finalize unwrap function, and that will verify that proof, and then it will transfer you your decrypted ERC-20 amount. And it also has a very important thing, which is that all of these decryption requests are one-time use. So when you go to prove these proofs that the Zama FHE VM gives you, it doesn't really care how many times you've proved it before. So inside the contract, we have just a little check there that says, hey, if this withdrawal has already happened, don't allow it to happen again. And then we have ERC-7984 RWA, which is for real-world assets. It just combines a lot of helpful features for use with real-world assets. So for example, it is pausable by an admin, so you can pause all transfers. Of course, there's minting and burning capabilities also from the admin. There's a block list or allow list functionality, which allows you to, block or allow certain users for KYC compliance purposes. There are forced transfers. So if you're an admin and you found that somebody is doing something bad and you want to stop them, or you just want to start moving tokens around for some reason, you can do that. And then there are freezable amounts per address, and these are confidential. So you can freeze a confidential amount of somebody's balance, and that will prevent them from moving it. And this just allows you to have greater control and, again, compliance. It all centers around compliance. So we've got some security concerns when we're dealing with FHEVM contracts. So here are a couple that we've started noticing are common. You need to be careful, of course, with your allowances when you're allowing somebody to manipulate an FHEVM, encrypted value. Once you've done that, they have it forever, and they can give that access to other people, unless you're giving them transient allowance, which is just for that specific transaction. So yeah, keep that in mind. Be very careful who you give allowance to, because they can basically see that value forever now. And also, I believe it's in here somewhere else, but you need to give allowance every time there's a new pointer created. So for example, if I send my tokens to you, my balance will be updated and I'll have a new pointer or handle. So, you need to have allowance for that too. Make sure that you only allow decryption and withdrawals once, unless, you don't want that. Don't let people withdraw twice. FHE operations can fail without reverting, so don't assume success. Take a look at that success and do something with it. Don't expect your sender recipient to be hidden. You're probably going to have to decrypt if you want to integrate with DeFi. There's a little star there because that's an open problem. If you're smart and want to work on this, come talk to us. And keep in mind that decrypt requests become public. So secure design principles. If there's any values that are entangled, any associated pointers, for example, in an AMM, if I am trading token A for token B, you're going to want to update 4 pointers. That's the AMM's token A and token B balance and my token A and token B balance, so that it hides what direction the swap was in, and how much I might have got. You need to consider allowances every time you make a new pointer, which is really often. There are a few FHEVM functions which will revert if you pass in an uninitialized pointer, like not and neg. Star, because that's being worked on, should be gone in the future. Use token transfer callbacks wisely. You're giving control over to someone whenever you call back into the contract. So when you transfer to somebody and you have like an on-transfer received hook, just only give that to contracts that you trust. You should understand privacy limitations. The addresses are visible. This using decryption invalidators is how you solve the problem of one withdraw per decrypt. Basically, just have a flag that says, yeah, we've handled that set of signatures. And there is a maximum amount of FHE operations per transaction. If you exceed that, your transaction will revert within the EVM. So just keep that in mind. It's not exactly a fixed number. It depends which ones you're doing. But you can find more about that in the Zama docs. Thank you.